Good morning. Can you hear me?
We can.
Okay, thank you. Yeah, so we are going to continue with our look at how to use Boolean algebra. Yes, guys, thank you. And we were looking at, we have looked at 5 gates so far. The AND gate, which is A and B. You can also write it as AB. Then the OR gate, which is A or B, and the NOT gate, which is the complement of A or whatever. And we have also looked at the NAND gate, which is A and B NANDed, and the NOR gate, which is A or B ORed. Or NORed, so to speak. We can say that these are NORed when we are speaking. So we already said that A inverse or B inverse is not the same as A or B inverse. These are never the same. And also AB, the whole thing inverse, is not the same as A inverse individually and B inverse individually. So I just wanted to start with this because what we are going to look at next is actually how to deal with matters of this nature. In our look at this, we are going to look at another couple of gates in the next chapter. But for the rest of this chapter, we'll continue to look at just these 5 gates. And really the focus here is to make sure that we understand Boolean algebra. Of course, it is not very difficult, but now we are going to start looking at some big equations. Already created some circuits, so that's okay. But the idea with this chapter is to give you all the tools that you need to deal with any problem that involves Boolean algebra, at least based on these 5 gates. Let us look at some Boolean theorems. The first theorem is that X is 0. Obviously, anything ANDed with 0 is 0. Remember, for the AND gate AB, and our output is X, 0, 0, 0, 1, 1, 0, 1, 1. So all of these will be 0 until we have everything as 1. So whatever X is, as long as it is ANDed with a 0, we already know that. The next one is X ANDed with a 1 is a 1. Meaning that if X is 1, you have 1 and 1 giving you 1. No, actually it is X, sorry. X. So if X is 1, then you have 1 and 1 giving you 1. If X is 0, you have 0 and 1 giving you 0. So if you have a 1, the output will just be equivalent to X. And actually, if you notice these two theorems, this one is like a gate, okay? So if this is a 1, then X goes to the output. If this is a 0, it inhibits X from going to the output. So that is something we talked about before, where I said that sometimes you can use your input as a control input. So clearly here, this value, either a 1 or a 0, is a control input that allows X to either go to the output or inhibits it. Another one is X and X is X, basically. So if you have 1 and 1, you're going to have 1. If you have 0 and 0, you're going to have 0. So that is another theorem. And finally, X and X inverse is definitely a 0, because if X is a 1, then its inverse is a 0, and this will always give you a 0. So these are some simple theorems. Here we have the O. This was the AND side. You can see the gates. This is the O side. X or 0 will give you X, because if X is a 1, 1 or 0 is a 1. If X is a 0, then 0 or 0 is 0. So if you're using the OR gate as your control input or as your control gate, then you can make this a 0, so that X, just whatever X is, it goes through to the output. Now, X or 1 is always 1, because we know that whatever this is, as long as we are ORing with a 1, as long as one of the inputs is a 1, our output will always be 1. Then here we have, so here you can see we have the same input going in here and there. So that is X or X, and this is going to be X. Because if you have 1 or 1, it is 1, 0, or 0 is a 0. And then this is X or X inverse. It will always be a 1. Because if this is 0, that's a 1. If this is a 1, that's a 0. And we know both these combinations will give us a 1. So these are some simple theorems that we already know that apply to Boolean algebra. Let us look at others. These are really similar to general algebra, ordinary algebra. So if I have A or B, it is the same as B or A. It doesn't matter which one I add first. If I you have A or B or C or A or B, or and C is the same as C, and A and B is the same as B and A and C. It doesn't matter. Okay. No, what you mean, Musa, but I think, yeah, probably you got that. So then we have these ones. Okay. I don't know what these are. Some are associative, some are commutative, some are, you people have been in high school recently, so you know this. But you can see Y or Z, it doesn't matter which two you start with. It really doesn't matter at the end of the day, it is similar to that. Same as if you are ANDing, okay? So X ANDed with Y and Z is the same as X and Y and Z. But we need to be careful if we are ANDing, if we are dealing with a situation which has both AND and OR. So X in Y or Z may not be the same and shouldn't be the same as X and Y. Sorry, it is not the same as X, Y, or Z, okay? So in that case, where the bracket is might matter. But when everything is or and, the brackets do not matter. Now you can see here in this one that we basically expand the brackets the way you do in normal ordinary algebra. So it's WX, sorry, WY, or WZ, or XY, or XZ. So exactly the same. Then we have these three. These three are interesting, and sometimes you really have to record them. So X or XY is the same as X. That is really important. So let us look at X and Y, and then output, which we can call Z. Okay, you have 0, 0, 0, 1, 1, 0, 1, 1. Actually, if we want, we can also put XY here. Okay, let me just say XY, and then I can have my Z output there. So 0, 0, XY will be 0 here. XY here will be 0, XY will be 0, and then 1. And then our term is actually, if you look at 14, our term that we are doing is X or XY. So it means I'm ORing this term and that term, and we can see 0 or 0 is 0, 0 or 0 is 0, 1 or 0 is 1, and 1 or 1 is 1. So if you notice here, actually what happens is that now X is equal to Z, right? So that means that if you have a term like X or XY, it is essentially the same as X, okay? That is how, that is a theorem that you would need to recall, because you see the problem is that if you meet it in a Boolean algebra and you are trying to simplify, and you cannot identify that this term is actually equal to X, then you are in trouble, because what you're going to end up with, actually, even if we use the Boolean algebra, we get there. Let's look at, you have X or XY, and that is X bracket, because we can actually pull out, you realize that we can actually pull out the common terms. We are going to have 1 or Y. And if we have 1 or Y, it is 1. It doesn't matter what Y is. If Y is a 0, we still have a 1. If Y is a 1, we still have a 1. So you end up with X anyway. But I wouldn't necessarily care for this step. As long as you can identify that this is equivalent to that and you jump straight to that, that's okay. So that's a little bit easy. But these two students tend to forget them. So then we have really to be careful. Let us look at them. We are saying that X or XY is equal to X or Y, okay? So let us try to prove if this is the case. XY, XY, and then we will see output Z, and we will also get X or Y to make sure that they are the same. 0, 0, 0, 1, 1, 0, 1, 1. So XY here will be 0. We are just adding that 0, 1. Now X or XY, I'm going to add X, sorry, not add or, X and XY. I'm having 0 here. I'm going to have 0 and 0, which is 0. 0 and 0. Sorry, X and Y, yes. Oh, it is X bar Y, yes. Yeah, sorry. I was starting to see the problem. So X bar Y, if Yeah, so that would be a 1 because x bar this would turn this into a 1. 1 and 0 will still be 0. 0 bar is 1, so it would have 1 and a 1, giving you a 1. Yes. And then that would be 0. And also that will be x bar will also be 0 here. So let us then add here, so or here. So you have 0 or 0 is a 0, 0 or a 1 is actually now a 1. And then x, which is 1 or 0, which is a 1, and then 1 or 0, which is also a 1. Let us look at what this gives us. X or y is a 0. Everything else will be equal to 1. So you can see that that term and that term are equal, meaning that x or x inverse y is x or y. The other one that confuses students is x inverse or xy, which is equal to x inverse or y. Okay, so this one, x inverse or xy is equal to x inverse or y. So you can also try and prove this one the same way. There's nothing different or ambiguous about this. But you need to, I don't want to say cram them, but you need to be able to remember them, because one day you're going to find a term like x inverse or xy, and you see here it is difficult to simplify. It's in fact impossible to simplify because you don't know, there is no common term here. Everything is different, but yet you should be able to know that this is x inverse or y, and that is the simplest term. So if you're doing something and you stop at this term, you lose a mark. If I'm giving 4 marks, I'll probably give you 3. If you take that next step and give me the simplified version, you get your extra mark. Just wanted to emphasize that. Now you should pull out your books or notes where you write, because I'm going to be giving you a few numbers to do. I also noticed that many of you still have funny names. Of course, we did it last time. Somebody is called Braun. I don't know what Braun is. So if I give you a small homework and your name is Braun, you will not get marks. I know that some of you wrote to me about that, but I had mentioned it, that please make sure I can see your full names. So I've not yet got to it. If I can prove that that was your name, then I will give you your marks. But at the moment, if you still have a funny name, then clearly you don't run. Rogers, do you have a question? Rogers, do you have a question? Your hand is up. Okay, let's move on. So let me simplify a couple of these, and then we'll take it from there. I'll also give you a number to do. So you have A, B inverse C, or A inverse, B inverse, C inverse. And this, if you notice, if you look at these two terms, this term is common. So we can say B inverse in AC or A inverse, C inverse. Have we looked at a gate like this? No, but this is actually a gate. It is called exclusive NOR gate. So for it, it gives a high when the two terms are similar. Okay, so we call it, if you have your two inputs into the gate, is exclusive NOR gate. It is, we are going to be looking at these gates in future. We are going to be looking at these gates in future, but this one is written like this. Okay, so just to give you a glimpse, so you would have A and C, and this is exclusive NOR, and it gives an output that is high when these two terms are equal. So either they are both 1 or they are both 0. But at this point, since we have not yet studied this, we can stop there. And even if we had studied it, really this is the simplest form. Let us look at this. In that one, you can see that AB is common. So you can end up with AB into C or D. Now, if I ask you to draw for me this, you can see that we have an AND gate here, an AND gate there, okay? So you have A and B and C or D. So we have 3 AND terms, this term, that term, and that term, but that term is OR. So you could have something like this. We can draw our OR gate in which we feed C and D, and so the output here is C or D, and then we put this into a large AND gate, okay, where we can put A and also B. So you can see this would be a 3-input AND gate. But as we said last time, if you have only 2 input AND gates, you can still do this, okay? All right. Yeah, okay, so let us look at, okay, something like this is, you can see that you have B inverse, okay? You have AD, or, but actually A is also common. So you have AB inverse into, yeah, you have A, B inverse, and what you have is D or D minus. We know that D or D minus is equivalent to 1, because if D is a 0, then D inverse, sorry, is a 1. If D, all these will give you a 1. So you end up with A, B inverse as the simple. This one, we can say A inverse, so we are going to multiply through as if we are doing ordinary algebra. Then we have A inverse B, then BA, which can be written as AB, that's okay, and then B, BB. 0, because if A is a 1, that's a 0. If A is a 0, that's a 1. B and B is a B, because 1 and 1 or 0 and 0, you know, it will give you the same. So if you find a number B that is or ANDed with itself, you are going to end up with the same one. So we end up or AB, okay? I just started with that term. Now we can see that B is actually common throughout, so we can have B, we end up with A inverse or 1 or A. And the moment we have a 1 here and we are ORing, we are going to have the whole term as a 1, meaning the simplified version is a B. And yeah, finally, I'm going to give you some numbers to try. Finally, you can see that we have reached another third one, which is here, CD is common. So you end up with a term here A, and A inverse B. Now, if you remember our theorems, this feels like this is actually the same form as X or X inverse Y, which we said it is the same as X or Y. So this is where now you need to realize the theorem. Otherwise, if you don't, then you'll stop at that point, and that's not good enough. So you end up with CD into A or B. This is how that term will be simplified. Any questions before we go and look at some examples that you can do? Okay, if there are no questions, I'll give you a couple of numbers. for you to try. You try those. Those are 3 numbers. You try them and we will see. We'll see what you get. Okay. Some people have AC inverse. Okay. So if you have AC inverse, you don't have to type it here. But since some people have finished, so let us do it. So this is, we can see that CD is the same. Oh, but we did this, so this is okay. This is the one I did. So then it means this is AC, AC inverse. Let us do it. So we can see that AC inverse is common. So you have 1 OB and 1 OB is 1. So you have AC inverse. And then for this one, I'm seeing some answers are saying A, B, C. One is saying this one. I believe this one is wrong. Another one is saying AC inverse. I don't know how that is going to work. Another one is saying ABD bar. I don't know. Let me try to do it, but it is quite easy because you can see that you have A inverse, B inverse, and D inverse. And this is inside here, you have C or C inverse. C or C inverse is most definitely a 1, because if C is a 1, C inverse is a 0, you know, so that's, so you end up with A inverse, B inverse, C inverse. So for those of you, yeah, so Monica has it. Nava Daphne, how do you people work in such noisy environments? So all of you who are saying things like not ABD are wrong, because these are individual. You know, if you say not ABD, it's almost like you're saying it is ABD, the whole thing noted. No, these are individuals. So it's important that, especially if you're texting in the chat, you know, you can say A inverse, B inverse, C inverse. If you say A, B, C inverse, these things are not the same. Okay, let's move on. Okay, there are some hands. Segawa, let me start with Segawa.
Yeah, sir. Clarification on this first one you did. You got A C inverse.
This one here.
No, the one we just did. Those two we have just finished. This first one here.
This one.
So we have A C inverse as the answer, but I'm wondering how did this 1 plus B disappear? Because this is 1, not so. In the bracket, you remain with the 1, not so.
1, yeah. So if 1 or B is 1, right? At least we agree on that one. And then you have A and C inverse and 1. Yeah, anything ended with the 1 is that thing. Remember? If we can come back here, anything ended with the 1, X and 1 is X. So the 1 always disappears. If it was a 0, then it would make everything 0. If it's a 1, it just disappears, okay?
Thank you.
Paul, Paul, can you ask? You had a question, Paul Waliaula. Paul?
Excuse me, sir. For me, I have a question.
Yeah.
Now, this question where we have y equals a bar, c bar, c and d bar plus a bar, b bar, c bar, and d bar. Seeing we have got a bar, b bar, and c bar according to the resolution you have done. Yes, that one. But I think.
Oh, it is D.
Yeah,
it is D.
D. Yes.
Yeah. It is a D. Sorry. Yeah, that was a mistake. It's that. Sorry. Okay. Then Daphne Kabago.
Excuse me, sir. As requested for the clarification on the first number for x equals to SB plus that one. Yes, I'd like requesting for some clarification on that.
Okay, let me do it again, just quickly. So you see, in this case, A is common, C is common, and D is common. So you have AC, and in here, you're going to be left with 1 or B. Is that, did we do that number before? Maybe with, which one?
But this one, which was SCD plus A bar, BCD. The A was bar, like it was, yeah. The A is not common.
I don't, the A is not common, or that one. So you have A bar, yeah? No. Let me try to do it. I thought I had done it, but clearly I haven't done it. So A is not common. What is common is C and D. We have C, CD. If we pull out CD, we are left with A or A inverse and B, right? You remember our theorem, this theorem here, this one here, which we said that X or X inverse Y is the same as X or Y. So if you see this term here, it is similar in that form. So it's written in that form, which is A or A inverse B. So that means clearly that it should be equivalent to A or B. And so we end up with CD, A or B. So now this is where I was emphasizing earlier that actually for you, when you reach this stage, you need to remember that actually I can use a theorem to simplify this further, because there is no other Boolean algebra that you're going to use to simplify this other than your knowledge of the theorem. But I hope that throws more light on that, definitely. Okay, then finally, definitely your hand is still up. There was a Daniel, I think. Maybe his hand is now down, so maybe I've clarified. Okay, so definitely you get.
Yes, sir. Thank you very much.
Okay, pleasure. Right. So let us move on and look at the last two theorems. I promise no more theorems. These are called Demorgans theorems. They are special theorems because they help us to decouple. They work mainly with the Nand and the NOR gates. Okay, so they are two. They are just easy. So if you have a term like A or B, and this has a common inversion, we cannot really simplify this unless we use De Morgan's theorem. Because if you have something like this, these are coupled together because of the common inversion. And so we decouple them. And the way we decouple them is actually if, and then you have individual inversions. So this is equal. And once you have individual inversions, then you can look at each term individually. If you had A, saying that that becomes A or B, but now with individual inversion. So from the AND, you go to the OR, and from the OR, you go to the AND. And if you want, we can actually prove this. So let us prove the first term, for instance. You have A, B, which is 0, 0, 0, 1, 1, 0, 1, 1. If we have A or B, we are going to have 0, 1, 1, 1. And A or B inverse is actually equal to 1. The rest is 0. And of course, we know that that is how a NAND gate operates, when NOR gate operates. Now, if we look at this term here, it is A, B, okay, 0, 0, 0, 1, 1, 0, 1, 1. Now, A inverse and B inverse are therefore going to be 1, 1, 1, 0, 0, 1, and 0, 0. Meaning that if I add these two, A inverse, B inverse, I'm going to end up with a 1, 0, 0, 0. So you can see that these two terms are now equal. That term and this term are equal. So it's easy for us to say that A or B, if this is fully together, it is inversed, we can have A and B with individual inverses. So let us look at some examples. Let us look at this one. Now, I want to tell you that every time you're doing a number like this, you should always start. It is better to start with the longer line. Sometimes you have something like AB or C. You have something like that. It is better to first of all look at that longer line, the longer inversion, and you get back to, but even if you know how to do this stuff, you can start with the short ones, but it can get confusing. Maybe with time, it will become clearer. But generally, as a rule of thumb, start with longer inversions. In this case, we have one inversion, and this inversion is over the all. Okay, so that means we are using 16. And so you're going to end up with A, B, inverse, or C. Not or C. You're going to end up with A, B inverse, but because we are ORing here, now we can AND. So we have AND C. And now we have our individual inversions. Remember, we are looking at this as one term, okay? And that as one term. And so the O changes to the AND, and then we have an individual inversion over that term. But the problem is that this term, they are actually two terms. So we can now apply 17 to this term, and we are going to have A or B inverse, okay? And now we put our individual inversions, okay? And C. And if we do that, we end up with A inverse, or obviously this is B double inverted. If you double inversion, you haven't done any inversion at all. So A inverse or B and C. All right. Is that clear? I hope that is clear. Is the theorem still the same if there are more than two inputs? Yes, Edwin. the theorem stays the same whether they are 10 or 100, as long as they are, we are going to be looking at some bigger at some bigger terms. So probably that went quite quickly. So I want to just do it again before you guys raise. Okay, you're raising your hands. I'll get back to you in a moment, but I just want to do this again. So we have A and B, that's inverse, or C, and the whole thing is inversed. So we are going to start looking at this long term, and when we look at that long line, we can see that the OR is here. Okay, so we are going to make this an AND gate, and on this side we will have C inversed. Okay, it's like we break down that line into these different terms, and our other term on this side is AB inverse. It will also have an inverse. Now we still have a situation where we have two terms under the inverse, so we need to break it down apart as well. And because for it it's AND, we are going to make it OR. We have a term here which is B inverse, we put its inverse, and the term here which is A, we put its inverse. This is double inverse, so it will disappear the inverse and C. So you end up with A inverse or B and C inverse. Okay. So I know that there are, let me see, a number of people had put up their hands. Do you still have questions, or have you understood now?
I understood.
Okay, thanks. Now let us look at also this one, which is A inverse or C. A inverse or C, and B or D inverse, and the whole thing is inverted. So when you're looking at the whole thing is inverted, you're looking for which terms are actually inverted. It is this term and that term. So that means that we are going to use the theorem that has an AND on this side, and we are going to create an OR case. So we're going to have OR. This term will be B or D inverse, inversed, okay? And this term will be A inverse or C, also inverse. It's because we have broken that big inverse into like two. So that's why this term on the right is inversed and the term on the left is also inversed. Now we can see that we still have a case here where we have two terms under the inverse and two terms under the inverse here. So we break it down, but now it will be AND. Okay, so you have A and A inverse, inversed, and C inversed, or here B inversed and D inverse, inversed also. So we end up with A, C inverse, or B inverse, D. Okay, so it's quite simple. Now the guy who was asking about whether we have many terms, if you have A and B and C and D and the whole thing is inversed, using Demorgans theorem, this is equal to X inverse or A inverse, sorry, or B inverse or C inverse or D inverse. You know, as many terms as you want, it does not change the meaning. So the question that Mugume is asking is, what is the output of A or BC, okay, and D or EF, and the whole thing is inverse, okay, although he has put another bracket here, but the whole thing is inverse. So we want to break down this inverse at this point. So we are going to have A or BC, and this is quite complicated, or, okay, so we inverse that, or D or EF, also we inverse that. Actually, these two terms are similar, so we can continue with one term. Then here we need to break this up. So we are going to have A inverse and BC. Now BC is inversed as one term. All right. Then on this side, we have D inversed and EF inversed as one term. Now we still need to break this down. So we are going to have A inverse and B inverse or C inverse. Exactly. Or on this side, clearly D inverse. In this case, it will be E inverse or F inverse. And that really is the final. You can expand it, but it won't change meaning. So that is where you stop. So yeah, so it's also a good example to show how you can apply Demorgans theorems. Okay. So I'm going to give you what is the difference between that and that. He's asking what is the difference between A inverse, B inverse, C inverse, and ABC, the whole thing inverse. The difference is very clear. In one case, on the left side, the first term, you first invert the inputs and then AND them. On this side, you actually first AND the inputs and then invert the output. So the output, the terms are not the same. Okay, the output could actually come out the same because of a coincidence, but the terms themselves fundamentally are not the same. And this is something. In fact, if we break this down, it will become A inverse or B inverse or C inverse if we are using Demorgans theorems. So clearly this term is not the same as that because we are using OR gate here we are using AND gate. Okay, can we do this term? Yeah, it's quite interesting. I don't know. It's quite big, I imagine, but try and do it. Tracy?
For the other explanation that you have just given,
This one.
the part where you say that the inverse, that where, okay, I want to ask, does the product of the, does the output, will the output be the same?
Here?
Will the output, yeah.
No, it cannot be the same. It's because you see here the outputs are either a 0 or a 1. So every time you write your answer by guessing, you already 50% probably by chance. You have a 50% chance of being right, even if it's complete guesswork. So it is true that the output could be the same because of some coincidence, but sometimes it will not be the same. So if you are doing what is right and what is not, and in this case, you can see these two terms are not the same, so they can produce different answers, right? Sometimes. Is that clear, Tracy? So yeah, so we need to be very clear that, let me do, as I know some of you probably have this, but let me do something here. We want to see AB. Is it the same AB? Is it the same as AB? So we have AB, okay, 0, 0, 0, 1, 1, 0, 1, 1. A inverse, B inverse. A inverse, B inverse here, it is a 1 because everything goes to 0. And the rest will be 0 because you have, at least in this side, you always have a term that is a 0. And because we are ANDing, then we have A and B inverse. What about A and B inverse? A and B, if here A and B is a 0, if we inverse it, we get a 1. The rest, here A and B is a 1, we are going to get a 0. A and B is a 0, we are going to get a 1. Because you can see that in this case, something is going to always be a 0. So if we inverse it, we get a 1. A 1. So you can see that these two things are not the same. Okay, Ta? So
good morning.
I'm
Good morning,
seeing
sir.
morning. I'm seeing AB or
What
CD or EF.
uh,
Yes, please go ahead. Go ahead.
what would happen if we had
Mm.
okay, if one of those AND gates was an OR gate. So if you had like A or B, A inverse, B inverse, or C, then the other one stays as an and the whole thing is inverse.
B inverse,
So if you have A or B inverse, then and C or C D
A
inverse,
or B.
then you have no A B, yes,
inverse.
inverse. Then you have the and C
or
D
D.
inverse, and then you have or E F inverse. Yeah, the whole thing
Inverse.
is inverse. Then the whole,
we can, let me first look at this, then we can come and see how to do with that, to deal with that one. Make sure that everybody has got this. So as you can see, these are three terms and they are added together and the whole thing is odd. So we are looking at these terms individually. Three terms, we are going to break our inverse at that point, meaning we are going to end up with AB inverse. We are going to add an inverse that we have broken from up, or because it was ANDed, so now we use or. CD is already inversed, we add that inverse, or EF, which is already inversed, we add that inverse and we end up with that, okay? So in a way that became very simple. If that is the answer that you got, you are right. Demorgans only considered inverse. I don't know what you mean.
so your microphone is muted. Can't hear what you're saying.
Oh, okay, thank you. I was just trying to explain that a situation like this is very difficult to come up with, because how do you come up with? Let's even use a simple, let's say A inverse and B inverse and C inverse, and then the whole thing inversed. This is actually equal to, you first inverse A, then you inverse B, and then you inverse C, right? And then you AND them. Okay, so that is A, B, C, and then after you inverse them again. That is how you get that term. Now my question is, how do you get a term like A? How do you get a term like A inverse and B inverse or C, no, or C inverse, and then the whole thing inversed? It is impossible to get a term like this because, I mean, how are you going to smuggle in the O? You get it? Because these three terms are inversed together. It is very, in fact, if you should go and try and create that circuit, you will realize that it is impossible to create a circuit like that. So that term that you are worried about, Oketa, hopefully you'll never find it. Emmanuel, do you still have a question?
Yes, doctor.
Yes.
Good morning, sir.
Morning.
Now, the challenge I'm finding is on the first, where we're working out on the AB inverse, then and CD inverse, then and EF inverse, then all inverse. When we break it down, we get AB double inverse, or CD double inverse, or EF double inverse. I was of opinion, why are we not even breaking it more? Then we have A or B.
Now let me stop you right there. If we have AB, inverse and an inverse, already this double inverse means that actually we have AB, right? But let me try to entertain what you are trying to do. If we have AB, inverse, and we take the first inverse, we are going to end up with A, inverse, or C, inverse, and again what? And B. So that is B, inverse, isn't it?
Yes.
And if we take that down again, we are going to end up with A, inverse, inverse, and B, inverse, inverse, which is still AB. Okay. So you would have gone through steps that are not necessary, but eventually you reach the same point, right? Okay. Tracy?
I wanted to ask, according to this question, we have an expression for x. So what I wanted to ask is, when we simplify it using this theorem, for example, this one, we got AB plus CD plus EF. When we input
CD or
values,
EF.
sorry, okay, yeah. So when you put values, will I get the same answer as I would have if I had not simplified it using this theorem?
Very good question. Let's do it. So we have AB and CD and EF, okay? And on the other hand, we have AB and or CD or EF. So let us imagine that A equals B equal to C equal to D equal to E equal to F. In fact, let's just say everything is equal to 1. So you're going to have 1 and 1. No, you're going to have 1 and 1 inversed, and 1 and 1 inversed, the whole thing inversed. 1 and 1 inversed is a 0 and a 0 and a 0, the whole thing inversed. Okay, so that's a 1 and 1 is a 0. No, 1 and a 1 is a 1, inversed is a 0. 1 and 1, you know, okay, so at the end of the day, we end up with 1. Let us look at this one. A and B is 1 and 1, or 1 and 1, or 1 and 1, which is 1, or 1, or 1, which is 1. So yes, you do end up with the same answer. This as long as, by the way, it's good Tracy brought this up. As long as, if I give you a question to simplify and you want to prove if it's right, you can throw in some numbers, some bits, and you see if you get the same. Because if you have done your Boolean algebra correctly, you should get the same answer, because we are just simplifying. When we simplify equations, we are not changing meaning. We are just using fewer terms. The reason why we simplify is to use fewer gates, make smaller circuits, use less circuit board space, and so on and so forth. Okay. Good questions. I appreciate the discussion, actually. By the way, let me ask you, are you at campus? Are you physically at campus? First years?
Yes, we are.
Oh, nice. But I've been told that you prefer online, so we'll do online for a few more weeks. Mwine Benjamin prefers online. Some of you probably just want to stay home. No, it is not a case of voting. I'm actually currently traveling, so I'm not available physically, but once I'm available physically, we will see if it's necessary to stay online or not, and that might be in the next couple of weeks. We'll make that decision, but for now, let's remain online since it's going well. Okay, maybe before the
excuse me, lecturer.
Yes.
I wanted to speak a bit for computer year 2, that they have internship going on with the semester, so we are requesting that we stay online, also considering that.
Okay, you're breaking, but I imagine you're in second year.
I beg your pardon.
Are you a second year?
Yes.
Okay, so yeah, okay, great. Thanks for letting me know. So yes, in this class, second years, and of course some retakers, and people are doing internship, so they may not be available to take classes on campus. But I will probably teach one physical lecture towards the end of the semester, just to meet you guys. And it's not that I know everybody, but at least you know me. But
yes,
stay online, it is better for everyone. Thanks for letting me know. Let's continue. That was supposed to be a break. Okay, so now I wanted to give you something to do, Demorgan, something for you to just experience as well. But where is it? So anyway, yeah. Anyway, we'll meet them. It looks like I can't find them. Let's just carry on. I will hopefully find something for you to do. But let us look at the implications of Demorgans theorems. So if you've noticed, Demorgans theorems, basically this one is like it is like the NOR. It is the NOR gates. And we know how the NOR gate, it is an O with a bubble. This bubble essentially means an inverse. We have already looked at this. So we are saying that this term is the same as that, because if we are saying this is equivalent to that, and on this side we have an inverted x ANDed with an inverted y, so you have your AND here, and you first invert these terms, and you end up with that. So we are saying that these two terms are equal. In fact, this is an equivalent gate. Okay, so instead of writing this, we can write it, or we can draw it as that. We have two bubbles here, which means inverse, okay, x, y, and then here we have our output, which is x or y. So this is an equivalent NOR gate, okay, and sometimes we use it. And let me give you some rules, how this looks like. When you are writing a thing like this, you look at the sign. This is O. So already if it is O, you write the AND shape. And there is a bubble here. So you remove it and you put it where it wasn't. So on the outputs, they were not there, you put them. On the inputs, they were not there, you put them. On the outputs, you can see it was there. So here, you remove it. What you have created actually is what we call an equivalent NOR gate. Okay, is that clear? We are going to use these you know, sometimes where we use equivalence, we need to be able to draw equivalent gates, and we are going to use them later on. So it is important that you understand them. So for instance, if I have an OR shape, there is nothing that really will be similar to an OR. Of course there is, and we are going to look at the universality of these gates. But in general, if you have an OR gate, NOR gate, you can rewrite it in this shape by putting bubbles where there were no bubbles and removing bubbles where there were. And of course, changing the shape. So if it was an O shape, you make it an and you can see there are no bubbles here. So you put them, and there was a bubble here, you remove it. That is as simple as that. Let us look at this case. This case is a NAND gate. So you have, this is in total is a NAND gate. It means you have X and Y and you inverse them here. Now this is similar to, we have X, Y inverse. This is similar to, if you look at this term, you OR two inverted values. So you have an OR gate here, and then you first invert X and you invert Y, and you have an equivalent. So you end up with an equivalent gate. If this is the one I'm trying to write its equivalent gate, I see it is an AND shape. So I'm going to create an O shape. I see that there are no bubbles here, so I put them. I see that there is a bubble there, I remove it. I put the bubbles here. So this is your input side, that is your output side. But if you look, this is similar to that, because you have your bubbles on the outside and nothing on the output side. Bubbles on the input, no bubbles on the output. Okay, so that is just an equivalent representation, and we are going to see its impact. But this is can be like an implication. Let us look at something. No, there is somebody who is talking. Amanyiri Stevens. Amanyiri. I mean, guys, if you are not in class, you don't have to attend. Eh? I told you, me, I don't record people who are here. I don't even really mind if you don't understand, but at least do not disturb the class. So let us look at this. What is this? This is C inverse. So here you end up with A, B, C inverse, and an inverse, right? And this we have already seen is going to be A inverse, or B inverse, or C inverse with another inverse, which is A inverse or B inverse or C. Okay, yeah, thank you guys. And just to re-emphasize, if I have a gate like this, which we know as the NOR gate, it is similar to, I change the shape. There is a bubble here, I remove it. There are no bubbles here, I put them. If I have a gate like this one, if I want to get the equivalent shape, the gate, or a different representation, I make the O shape and I put bubbles where there were no bubbles. We are going to be using this later on, just we are going to be creating statements out of our Boolean expressions, and you will realize that actually it is quite important to know how to write these equivalent forms of the gates. Okay, so I think you can do this. Let me not waste time. Let's just do it. So we are going to have A inverse and B inverse with another inverse, and CD. C is inverted and the whole thing inverted, which is A inverse and B. And if we look look at this one, we are going to end up with C inverse with an inverse, or D with an inverse, and that's ORed, which ends up with A inverse B and C or D inverse. And you can stop there. Right. Now let us look at the universality of Nand gates and NOR gates. Let's start with the NAND. Then the universality means that you can actually use NAND gates or NOR gates to perform any Boolean functionality or any Boolean expression. So even if the Boolean expression has A, let's say something like A or B, and you don't have an OR gate, because here you need an OR gate, but you don't have an OR gate, you can use a NAND gate, or you can use an OR gate to perform. So that is that's where we say that they are universal. We really mean that they can actually perform anything, much as even if it's AND, even if it's OR, even if it's an inversion, an AND gate or an OR gate can perform it. So in that context, they are universal. Let us look at an example, or let us look at the universality of these. The first one is this one. If you have an AND gate and you feed it the same value, which is X, it means that the output here, you're going to have X and X inverted, isn't it? Because otherwise you would have A and B inverted. That's how NAND gates work. And this is actually, if we use Demorgans, we are going to find that it is X inverse or X inverse, X inverse or X inverse. If you OR the same, something with its own, with the same, you end up with the same. So we end up with X inverse. So that means here we have X inverse. So I have my output, and now, sorry, my input is X, my output is X inverse. That means that if I did not have an inverter, so X inverse. If I didn't have this gate, I can use the NAND gate in that way to get my inversion. And you can see there, it is equivalent to the inverter. Now, for the AND gate, let me just create a new shape so that we can go through this. We don't have to rush through this. Okay. We can have an AND gate. Okay. We have our terms A, B. We have that. And then pass the same output through the two inputs of the NAND gate, another NAND gate. Let us see what this one gives us. So if we have A and B, that means we have A and B here, also A and B there, inverse, of course, because this is the one that comes from the NAND gate. So it means that the output here, we are going to have A, B, and AB, like that. And if we break this down, we are going to have AB or AB. We already said that if something is ORed with the same, it is that value, which is A, B, It means that actually by connecting our output, by connecting two NAND gates in this way, we have ended up with an AND gate. X equals, right? So that is universality. If I'm doing something and I don't have an AND gate, I can use AND. Unfortunately, of course, you end up using two gates, but sometimes, as we are going to see later on, sometimes it's possible to simplify things. If I want to perform the OR rule, I can connect my AND gates in this way, my NAND gates, A, and I put another NAND gate, and the B goes into both inputs, the A goes into both inputs, and then I will put this through another NAND gate. Let us see what we end up with. Here we are going to have, we already said, A inverse. Here we are going to have B inverse. That one came from, you remember here, okay? So if you pass a value through both inputs, you just inverting it. And then here we're going to have A inverse and B inverse inverted again, which is equal to A inverse inverse or B inverse inverse, which is A or B. So what we have done actually is that by connecting our NAND gates in that way, we have performed an OR, A or B. So you can see that it can perform these NAND gates connected in a way, in a particular way, can actually perform the 3 basic Boolean operations. That makes them universal in that context. It means you can generate and create a whole circuit that does not contain any OR gates or AND gates or even inverters. It only contains NAND gates. If there are no questions, we can look at the OR gates. The NOR gates are also universal. Okay, so the inverter is connected the same way. You just use one NOR gate and connect your input into both input terminals, and you'll get your inverter. Now the difference here is that the connection for this case is a little different. For the OR gate, we have the 2 NOR gates connected in that way, and for the AND, we have the 3. Okay, so the shapes change a little, but it's okay. You don't have to cram these things. You can always, usually actually when I ask a question around this, I'll give you the shapes. So because I don't believe in cramming something that is in the book. So you don't have to cram the shapes. I'll give you this. Okay, I promise if I ask a number around this, I'll show you these equivalent shapes. But in general, you just need to know that you can connect your NOR gates or NAND gates in a way that performs the 3 basic operations. Okay. Now let us look at some examples. So we have an example, X is equal to AB or CD. If I give you this term and I tell you that you do it for me, implement it for me, you would see that you need an AND gate here, you need an OR gate, and an AND gate here. Okay, so you need actually 1 OR gate and 2 AND gates for you to perform this nicely. I've given you these 3 ICs, 74LS00, 74LS08, and 74LS32. If you notice, this IC integrated circuit has 4 OR gates. This one has 4 AND gates, and this one has 4 NAND gates. So the question is, how do you perform them? So you can choose to use 2 AND gates here. Okay, so you can use that one and that one if you choose, and then you just use 1 OR gate there. You don't need to use the 74LS00. The problem is that now your circuit has 2 ICs. If you are putting them on the circuit board, you need space for 2 ICs. Whereas somebody could actually use this, right? Somebody can use, instead of using these AND and OR, they can actually use NAND gates to perform those operations and hopefully end up using 1 IC. This is what we want to explore in this example. That actually by using NAND gates and benefiting from or taking advantage of their universality, you can actually end up using fewer integrated circuit boards, making your full substrate or your full circuit smaller, right? Let us look at this example. Here we have chosen to use AND gates, okay? So AND 1, AND 2, AND gate 1, AND gate 2, and then your OR gate to perform your thing. So that means you can use, let us look at the 74LS08, which is this one. So you can choose to use, these are the terminals that are connected. So AND gate 1 is connected to terminal 1 and terminal 2 as your input. So you put your inputs here and your output will come out of 3. Okay. And then when it comes out of 3, you can now come and connect it to one of the OR gates, maybe connect it to there that comes from 3. No, you can connect it to 1 according to what they've done here. Now for this one, they have also used, this is your AND gate 1. The AND gate 2 is 4 and 5. So AND gate 2, you can tell from the terminals 4 and 5. This is where you have connected your C and D. Here you have connected your A and B, and your output is coming out of 6. Okay, and this 6 can now be connected to terminal 2 on this side. This one was at terminal 1. That was output 3, output 6. So you basically are taking advantage of gates on these 2 chips to actually perform. And then the output here, the output at 3 should be actually simulating that. But you need both ICs, and you can see there are even 2 gates on this IC and 3 gates on this IC that you haven't used at all. Daphne?
Excuse me, sir. I was requesting for a explanation on that. Like, I've not understood.
Okay, that's okay. I totally oblige. I'm going to just make a duplicate of this and just redo it. Okay. This time a bit more slowly so that people understand. So I was saying that for you to implement this term, you can see that you need to AND these ones. Okay, so I said you need 1 gate. I've called it AND gate 1. You need to AND these ones also. I've called it AND gate 2. And then you need all the 2 terms. Or I can call it OR gate 1, but really it's just 1 OR gate. So you have you need 2 AND gates and 1 OR gate. Unfortunately, the ICs you have, these are, by the way, are called quad ICs. The idea of quad is that each has 4 gates, but they are the same type. You don't have an IC. You can have an IC with different types of gates, but in this case, we have been given a scenario where we have ICs. Each IC is a quad IC, and that really means it has 4 gates, but those gates are of the same type. If we had an IC that had, 4 gates, but at least 2 AND gates and 1 OR gate, then we'd have to use 1 IC. But unfortunately here, these 2 ICs, we have to use 2 AND gates from this IC and 1 OR gate from that IC. So if we look at this shape actually simulates that, okay? You can see this is your AND gate 1, AND gate 2, and then this is your OR gate, right? So we are going to get our 2 AND gates from this chip and our OR gate from that chip. And what I was saying is that if you look at these terminals, these are the connections they are telling you. A is connected to terminal 1, so that is A. B is connected to terminal 2, meaning that our terminal 3, you can even see the connection. This is our output. Let me call it M. So I can say M here, and that means if I say this is N, C is connected to terminal 4, D to terminal 5, and N comes out at terminal 6. Now you can see when we go to the OR gate side on this chip, M is connected to terminal 1, so M will be connected to terminal 1, N will be connected to terminal 2. By the way, these are called intermediate nodes. Okay, when you have nodes in the middle here, these are like intermediate inputs. They are hidden on the inside. That means our output, which I'm calling, which is X, is coming out of that. Connect this, and it's quite easy, really. You're just reading off of your ICs and just making physical connections. Now I should tell you that usually when you get these things, you can only see, you don't see the inside. You only see input terminals and output terminals. You never see the inside, right? When you're dealing with ICs. But diagram to know what is what, which Okay. So we want to see what if we used this? What if we used that? Let us see if we use that. I want to put this one here so that we can have, this is the AND gate. We are going to use NAND. So that is the AND gate. We are going to use the universality of AND, okay? This is the NAND. So if we want to AND, we connect our two terminals, sorry, our two gates in line. Basically, the first three terminals represent one gate. Exactly. Two inputs and one output. So let us connect. For the first one, we are going to connect two gates. Okay. And this one is going to be A, B. That's an AND gate. The output of that is passed through the next AND gate on both inputs, meaning here we are going to end up with AB, and then we need CD. Okay, that's C, that's D. Again here, CD. All right. So basically, we are now at that point. Okay, this is where we have AB and we have CD, and now we want to. If you remember the OR gate in terms of NAND, this is the term, a little bit complicated. For the OR gate, we get our NAND, okay? We pass it, we connect it like that, and another NAND, we connect it like that, and then we have that connection. So that would be like A, and that would be B, meaning that this would be A or B. Our case, we need to pass CD through here, CD, and AB through there. So we are going to connect this again. Okay. And we are going to pass this through another NAND gate like that. And then we will pass it through the final NAND gate, meaning that our output here should now be, obviously this is AB and CD. And what we are hoping for is that out here we have AB or CD, which is our X. Now, unfortunately, you see, we have 1, 2, 3, 4, 5, 6, 7 gates. So what have we done? We have a 7-4 ALS that is a quad. It has only 4 NAND gates, but it looks here like we need 7 NAND gates. Unfortunately, when you see these two terms, they are quite similar. Okay, you have done this and done that again. By the way, this is an inverter. If you remember that when we connect this, we are inverting. So it means that here, what did we have here? Here we had A, B inverted, and here we have AB. So if we have AB here, what do we have here? If we have AB here, then we have again AB inverted. How do we know? We have A, B, okay, through one side, and AB inverted, which is equal to, I think, AB inverted or AB inverted. And because these are similar, you end up with AB inverted, which is this. In other words, the value here, which is C, D inverted, is the same as the value here, which is CD inverted, meaning that we could have just done a direct connection and foregone these two. So in other words, this is equivalent to AB, here CD, and we pass this through that. In other words, we chop off these 4 gates and we will still end up with x is equal to a, b, or c, d. All right. Have you understood that? Yeah, so each IC would come with a data sheet with the information that you're looking for. Have you understood? What I did here was to create a scenario, sorry, to use Nand Gates to simulate what these gates would do. So I started with the AND gate for AB, the AND gate for CD, and then I did the OR gate here, which is ORing AB and CD. And then after I realized that actually in the middle there are gates that are not doing anything here. You see here you have CD. What this gate does is it inverts this to CD, and the next one inverts it back to CD. So I can forego those 2 gates and also those 2 gates, and I will end up with this one. And once I end up with this one, I can use just this IC to use 3 gates. I don't need to use the 4th one, but at least in the end, I've used 1 IC, not 2, in the case of using OR and AND gates. You see, so with universality of NAND gates, universality of NOR gates, you can actually end up with a situation where you benefit by ending, definitely you might end up using fewer ICs, but most importantly, you might also end up using fewer gates. But in this case, it's not the case because here you're using 3 gates and OR, and here you're using 3 gates NAND gates. You can do something similar with the NOR gate. It may not reduce though in that case, so the equation might have to change. If you change the equation, you might find scenarios where it reduces. But if you use the NOR gates, you use the NOR gates instead of the NAND gates and see if it changes. If it does not, that's okay. It just means that you haven't benefited from that reduction, but you still have a circuit that has only 1 type of IC, or sorry, of 1 type of gate, and that might benefit you by using 1 IC. Let me first ask Musa.
Good morning, Doctor.
Morning.
I'm like, what if we use Demorgan? Because me I see that X equals to A and B or C and D. Isn't it the same as X equals to A and B baba, like 2 bars, or C and D baba? Then I join them using Demorgans. Then I can use 3 NAND gates, only 3 NAND gates to form that circuit.
A, B, or C, D. And so you want us to say
then
A, B, or C, D. I put a double. Is that what you want?
No, not that. No, not that first. It is AB baba.
AB baba.
Baba, or C baba, like that. But then from Demorgan, I can join that.
So how do you join this?
It is now AB bar and CD bar and CD bar, then bar all over. Yeah.
Okay. And now what are we doing here?
Then I can use
So you can use your 2 Demorgans, 2 NAND gates. Meaning that here you have CD, here you have AB.
Then then I use another NAND gate.
Yeah. So you end up
that one
with AB and CD. Yeah. And that is equivalent to what we have just got. So what you are trying to do is to avoid all this mess, yeah? I mean, clearly it works. I just feel that working backwards in this way is if I try to emphasize this, a lot of students are not going to get it. It's easier, it's faster. And if a student can do it, okay, they can. But by the way, if I've probably asked for a question and said use equivalent, use Nand Gates to perform this, I probably want to see this step. I'll probably be giving a bit of marks, not a bit, a heavy marks for this space, for this stage, because I want to see if people actually can remove that. So if you forego it, I don't know how it would work out. You might end up missing marks because I really want people to understand the equivalent gates and the universality of these gates and how you connect them and what you come up with. So I can see that it works, but if I've stated the question saying use Nand Gates only, I probably want to see how you're using them because I'm giving marks per step. I always give marks per step. Another, Daphne, the students have reduced. I don't know, 10 people have disappeared. Daphne, you have a question?
No, it's all right.
Okay. Daniel likes this. It's definitely cool stuff. Digital electronics is really cool. It's really nice. And if you love it, you'll score 90%. In fact, this is the one course where you can score the highest marks you'll ever score in Makerere. But also it is the very one that really stresses people. I don't know why that's the case. Can we try an example where there is a reduction in the number of gates? Okay, so we have just tried it because you see we have reduced the gates, Patricia. Mugerwa?
From the previous, no, the modification we have been given by one of our own students. To me, it looks a bit, yes, this one here. There are very few NAND gates, but still, I'm still using NAND gates for the circuit. And in the case where we needed to use the ICs, the integrated circuits, I think this other example, the one given by the student, will be better to implement onto the IC.
No, but we have already established, Alex, that it is exactly the same because we have this circuit, okay? But using my long method of first principles, we ended up with this thing, big thing, but then removed 4 gates and ended up with this. In fact, this is what we are implementing, okay? We are not implementing this because this needs 7 gates and we clearly don't have 7 gates on our circuit. But there are some stages, this stage and that stage invert each other. So it's like double inversion. And we have said that actually we cut that inside out and we end up with exactly the same. In fact, what Musa came up with is very similar to what we ended up with. There is no difference. So at the end of the day, you implement it. I'm not saying that once you have this big thing, you stop there. You have got to investigate and see if there are some unnecessary stages or redundant stages that you can remove. If you cannot remove them, then that's okay. But usually there is a way you can reduce. So you should try and investigate that. Vivian.
Good morning, sir.
Good morning.
I would like a clarification on how you get how you got those many gates, because I did not understand it.
The many gates.
Yeah.
Okay. Yeah, now that's a question, and I'm really happy to repeat this because sometimes I get it, I bring it. So we have a scenario where we had 2 gates, 2 AND gates, and an OR gate, yeah? And we had AB and CD. Now we are saying that we want to use NAND gates. That means we need to use, when we have an AND, we use its equivalent NAND combination. It's not just one NAND, it would be a combination. If we have NAND combination. And we already saw those. We saw these when we were looking at the universality. So for instance, this is this is OR. Okay, so we can first put the AND gates, which are just, we write them in line, which is first AND gate. It is, we have, okay, and then we just pass the same output through another AND gate. We already said that, sorry, 0. We already said that this is equivalent to an AND gate. So we are going to do the same for CD. This is CD, and these two AND gates are equivalent. Sorry, these two in this combination are equivalent to another AND gate. Now the OR gate is connected in this way. So it is like AB, it's like A going through both inputs and B going through both inputs for you to end up with A or B here. So that means that, again, for us to end up with AB or CD, remember here we have AB. We need to pass it through an AND gate, both terminals, and also CD through both terminals, and then the output here will go through another NAND gate, both terminals. So essentially here what we have is X is equal to AB or CD. And as you can see, I've not cooked books, I've not used my own things. I've gone to the equivalent circuit, which is given here, which I said I will give you if I ask you this question, and just picked them and replaced them with my 3 gates and the OR gate here. Now we saw that actually yes, just want a different pen. Yeah, we saw that we said that here we have CD and here we have AB. It's AB inverse and CD inverse because that is an AND gate. Now here, what we have is actually CD, and also here it is CD. And we know that because we know that when we go through an AND gate, by passing the input through both terminals, we are just inverting. Okay, that is also known here. If you look at this, A through both terminals is A inverse here. Actually, you can take your time later on when you're revising and you go through this again just to make sure you actually get how we are moving from AB inverse to AB. And when we reach here, we are going to see that we are back to AB inverse because we have inverted again. This is an inverter, and that's an inverter. This is an inverter alone, and that's an inverter as well. So here we are going to end up with CD inverse, whereas here we have CD. So why we can take out this part of the circuit is because here we have CD, and here we are back to CD. Sorry, CD inverse. CD inverse. Here AB inverse, here AB inverse. It means that from this point, since I already have my AB inverse, I can just jump and connect to that. And from here, I can jump and connect to that point, meaning these 4 gates don't have to be there. You can leave them, but really they are just inverting and inverting again. So you can take them out and you'll end up with these 2 gates at the input, okay, which is AB and CD, and then these 2 gates at the, sorry, this 1 gate at the output. And what I was saying earlier is that in fact, this is equivalent to what Musa said. The problem with Musa's thing is that you are working backwards, and it's not easy for every student. But also when you do things from first principles, it's just better. You can't make a mistake. And as I said, I might be giving marks for these steps. So using that hacky way might actually cost you marks. Okay, so I hope I hope that I've answered you, and I believe I've forgotten your name, but I think I hopefully now I've gone through it again. How do we connect these gates with transistors? Actually, the gates are made of transistors, a number of transistors and resistors. So I don't know what exactly that means. Daphne?
Excuse me, sir. For your output, I'm seeing X is equal to AB or CD. I thought it was supposed to be X is equal to AB and CD.
It is AB or CD. We can do it, it's okay. So let us look at this. If we have AB, we know that out here we are going to have AB, right? Inverse and CD inverse. Now what do we get here at X? X is equal to AB inverse and CD inverse with another inversion on top that comes from this gate. And this will be AB inverse with another inverse, or CD inverse with another inverse that comes from there. And we are going to end up with AB or CD. So you can see that our thing actually works much as we have simplified it. And so these guys of the book have used the colors. I didn't want to show you this because I wanted us to do it ourselves, but it is in the book. You can see this is the AND stage, okay, the 2 AND gates, and this is the OR stage, which are the 3 NAND gates. And so you end up with these ones in blue. This point here, the signal at that point is the same as the signal at that point. So why should I have these 2 gates? The same thing here. The signal here is the same as the signal here. So why should I use these 2 gates? And so you can remove the blue gates and you end up with just 3 gates, which you can now connect using your quad IC of the NAND. Okay. I see it is midday, 4 past midday. Is your brain tired already? I guess your brains are tired. Let me not continue, but we will continue on Wednesday. I believe last time I was engaged. Sorry about that. But the thing with the when I online, what I've realized is that I move faster because most of the diagrams I don't have to draw them. Before, I would have to come in class and draw everything on the chalkboard. But now we are moving faster, which is fine with me. And so much as we are doing 90 minutes instead of 120, it's okay. We are moving at a pretty good rate. It also means that we cover a lot of pages every time we meet. So I encourage you to keep reading. Don't wait for the test. Please just keep reading. It will be much easier in future. Have a nice day, a nice week, and see you on Wednesday. Goodbye. And also Susan Chihembo, happy birthday on behalf of myself and of the class. Goodbye. Mungoma says, give us lecture 1 and 2. I thought I've been giving the videos. Yeah, I've been giving the videos, so they are somewhere. Okay, goodbye.